Chapter 7 stuff today, so pull out your sheets. Gonna do, I don't know if I marked this one 7.3 or not, but suppose a firm's total cost curve is 15Q squared. We're gonna jump right in. What did we leave off with last time? No, that was 7.
This is 7.
Yep, that's 7. That was 7.1 and 7.2, I think. Because we just did that little schedule, right?
Yeah.
Did I do the graphs with you guys? I can't remember. Yeah, did we do the general cost curves? Is that where we left, the last thing we did?
Yeah.
Okay. All right, so I think we're ready to just jump into this equation, which we haven't done before in principles class. So suppose the total firm's total cost curve is TC equals 15 squared plus 8Q plus 45, and the marginal cost curve is that equation. Find the firm's fixed cost, variable cost, average total cost, and average variable cost, part A. So, fixed cost, what are you looking for? $8Q, no. So we got total cost equals 15Q squared plus 8Q plus 45. The 45, why? Because it doesn't have the Q variable, right? So fixed costs don't vary with it. You're kicking yourself on that one, Adam? Yeah, so costs that do not vary with quantity, anything that has just a number over here that doesn't have a Q associated with it represents your fixed cost. So that's kind of your starter. If you want to be a little more fancy about it, and you might, maybe if it was a little more complicated function, but you might, to find fixed cost, let's just put fixed cost, FC. To find fixed cost, set Q equal to 0, right? Because then once you set Q equal to 0, total cost equals total fixed cost, once you do that. I'll put the T there. And so Q, this collapses, total fixed cost equals 45. And then, of course, variable costs are the things that do vary with it. Average, what do we want to do there? Average total, chance to redeem yourself, Adam? So average total cost. Total cost of the lemonade stand is $200. How do I find average cost if I sold 100 glasses? Divide by 100, right? So total cost equals 200. Average total cost equals 200 divided by the number of glasses I sold. They were $2 a glass. With the equation, we're going to do the same thing. So if we take total cost divided by Q, that gives us our average total cost. So then just write it all out. 15Q squared plus 8Q plus 45, all divided by Q. We get 15Q plus 8. Right, transform the Q's down. plus 45 over Q. You could write that raised to the negative 1 power if you wanted. All right, average variable. Take our variable cost, total variable cost divided by Q. I'm going to skip. Get 15Q plus 8. And that wraps up part A. Find the output that minimizes average total cost. Find the output that minimizes average total cost. Who's got that one? That's a tough one, by the way. Tough without knowing one little trick. Taylor, I want to push you a little bit since you're a math person. If this was our average total cost function, what could we do to find the minimum point if we're optimizing using some calculus? First derivative, set it equal to 0, right? Do some stuff like that. So that's how we might go about it if we had some calculus, but we're not doing calculus here. So look back to that graph I gave you, the last graph on Friday. What's true at the minimum point of the average total cost curve? It's equal to marginal cost. So find that. So on our graph, we've got marginal cost cutting through the minimum point of not only the average total, but also the average variable. So that's going to be kind of our slick way we can figure out the minimum point. Did you get an answer already, Adam? Oh, okay. So you've got the marginal cost curve. It was given to you in the problem. So marginal cost was 30Q plus 8. 30. Yep. 30Q plus 8. Yep. Graphically, we're doing this. So average total. Find the question says, find the output level that minimizes average total cost. You got a what?
675, but I'm not sure about
675? Okay. What else? Other people get some answers? So if we take this function, set it equal to this function, we should be honing in on this. Anybody else get an answer yet? Finding where marginal cost equals average total cost. Colby, what are you doing? Q squared equals 3. Okay. That's what you got, Taylor? Colby, how you rolling over here? 30Q, 15Q. Okay. So solve it. Bring the Q all to one side. All right. So then how would we deal with that? So we got Q squared equals 3. We don't want q squared. Is the square root, yeah. And we've got that. There you go, 1.73. Did you see where you went wrong with your 6.75, Blake? Okay. So 1.73. And then, so that's part B. We'll it's asked for find the output that minimizes, so 1.73. Part C, find the output level at which average variable cost is minimized. So we got the same thing going on. Marginal cost is cutting through the average variable at the minimum point. Zero, good. Yep, that's right. You guys get it all collapsing down? Everybody get that? So that's at 0, so it's not, again, this is all drawn not to scale, so sometimes we can't trust our graph, right? This is the generic graph, but the functional form here had average variable cost coming out, and if we look at the functional form, we see that, right? Look at the average variable cost equals this function. We're at a intercept and a q, so this is a linear function. And so yeah, and it can jump out a little bit differently. All right, questions on that? So that's just starting to deal with a little bit of P's and Q's here, a little bit differently with functions. All right, let's move on to the next one, unless anybody's got any questions there. So a little more detailed here. Steve and Sons solar panels has a production function represented by Q equals 4KL, where the marginal product of labor is 4K, the marginal product of capital is 4L, the current wage rate is $8, and the rental rate is $10. In the short run, the plant's capital stock is fixed at 10. What is the cost the firm faces if it wants to produce 200 solar panels? What's your thoughts on approaching this one? Part A, what is the cost the firm faces if it wants to produce Q equals 200?
Figure out how much labor we need.
Okay, good.
So the 200 is the original Q equals 4K though?
Yep.
So we know K is 2.
We know K is 10, yep. So go plug that into the production function, solve for L. L equals 5, sounds good. Everybody else get that? But the question asks for cost. So now what are you going to do?
5 times each.
Okay? What'd you get? Say that again, Blake?
Could we use that formula, the C equals wage times labor?
Yep, that's the only one to use. So that's our cost function, which from our previous chapter was our ISO cost function, right? So it's just the total cost. So total cost equals the wage rate times the labor rate plus the rental rate times the amount of capital. You sub those in, and what do you get? 140. You guys get that? It's important that you work through these on your own. It's a little different to just copy it off the board as opposed to engaging your brain and working through the details. Struggle through it now. All right, so we had capital fixed at 10. That was kind of the thing that started this problem off. I don't know why, Taylor. I just felt like showing you a couple of the derivatives here too. Total cost function, first derivative of this is the marginal cost, 30Q plus 8. And then same thing here with the marginal product of labor, first derivative. It's actually a partial derivative. Okay, yeah. Okay. B. You guys solved it already? Are you waiting for me? This is kind of an A, B. This is like part one. This is really A. B. What will the firm wish to do in the long run to minimize cost of producing 200 solar panels? How much will the firm save? Hint, you may have to review chapter 6 to remember how the firm optimizes when both labor and capital are flexible. Yep. So that's our optimal condition. So that's the thing we have to start off with. So you said MPL over MPK, and then what about further, Adam? MPL over MPK, I like that part, but what's the rest of the story? Equal to the wage over the rental rate, right? Now talk to me in terms of ISO cost, ISO quants. What is this saying? ISO quants, ISO costs, what's this condition stating, this optimal condition? In terms of the graphically, ISO cost, ISO quants, what do you? It's a point where the two are tangent, the two slopes are tangent. So on our graph, we had ISO quants. Here we were talking about an ISO quant of 200. And then we have an ISO cost line with a slope equal to W over R, right? So the slope of the ISO cost is equal to the slope of the ISO quant, which is the ratio of the marginal products, the marginal rate of technical substitution, and that gives you the optimal quantity of labor and capital. So that's where we start this problem, and I'll crank it through. This isn't. So you're setting this equal to the wage rate over the rental rate. The slope of the ISO, yeah. So put that, but now put in the actual numbers because we know that. Yeah. chunks here, so get rid of that. Maybe you'd want to just rewrite it, but because you're kind of disjointed here. Put that 8 over 10 there, and then solve for the optimal amount of one or the other, K or L. Yep, that's right. So let me park. Think about what that would mean to be putting that into there. Okay, 0.8. You lost a variable somewhere. Oh, you don't want to put in. We're re-optimizing, so don't put in the old amounts. We're kind of re-optimizing. So right now, that was the short run situation because capital was fixed, and that's what we're doing is we're going to find the new optimal solution for capital and labor. Yeah, that looks good. Okay. So it looks like most of you got down to the K equals 0.8 L. Okay, so then what did you want to do, Al?
Selecting chapter 6, on that, because we now know that K equals 0.8 L, we can do Q equals 4 times 0.8 L.
Yep. Yep. So now we can sub that information back into our production function. And we know that we're trying to produce how many units, I guess. Do we want to keep the Q? We wanted 200. So that information was known. So that's why we can break this down now. We've got this equation that shows the relationship between capital and labor. We've got 200 is equal to 4 times K, which is now 0.8 L times L. So now we've got one equation with L, and you can solve for L. What did you guys get for L? Like, question? Oh, I thought you had that.
So I just plugged in the old,
Oh.
I plugged in the old ones like you said.
Okay. No, so what I wanted you to do was substitute this, this for K, because K was 10, and L down here. So you've got 4K over 4L equals, and then you've got the 8 over 10, which is, yeah. So then if you solve that out, you'll get your K equals 0.8. Solve that for K.
Is it 7.9?
7.9, yeah, that sounds pretty good. Yep.
We sub those numbers back to the original rental rate and rate grade.
Yep. Then you got a little more work ahead of you. Oh. Okay. Did you figure that one? Got that? So you got down to there. Yep. And now just sub that right back into the point K equals 0.8 L. Yeah. Yep. You got it. So before we get too lost, let's go back and kind of review the question. What are we looking for?
How much will it
Yeah, so ultimately, how much will the firm save? Did you come up with an answer? What did you get, Taylor? $13.60. That's pretty darn close. There must have been some roundings. $13.50. The answer here says $13.42, so probably some rounding along the way. All right, so yes, this last step was then just to plug that back into the cost equation. And then we could compare how much this was running versus what we had before of 140. So the new cost was 126.58 is what this thing says. So and that was $8 times 7.91 plus $10 times 6.33. What's that?
I did 7.9.
Okay. Yeah. So we had a savings of $13.42, or again, if you did a little bit of rounding. Okay. Questions there? So last one, down at the bottom, we've got a long run, short run situation. Suppose that the long run total cost function for the firm is this function. So we got a cube in there, 22,600 q minus 300 q squared plus q cubed, and its long run marginal cost function is that. At what levels of output will the firm face economies of scale or diseconomies of scale? Hint, the cost function yields a typical U-shaped long run average cost curve. All right, so I want to review this a little bit first before we jump in. Does anybody remember what economies of scale, or if you did your learning curve, what was economies of scale? Who's got economies of scale? So, what's your gut feeling with economies of scale? What you remember? Is it good or bad for the company?
I would say it's
It's
good.
good. So yeah, that's a good start. Okay, why is it good? So it has something to do with as you increase the scale of production, meaning you scale up, you get to produce larger quantities. What do you think's happening? Your instinct is good, that it's good for the company. Good in what way? So as we start to get bigger and bigger, we scale up production, we're able to get some advantage of more profit, potentially, ultimately is what we want. Economies of scale doesn't speak specifically about profit, but it comes to us through reductions in cost. So as we scale up production, the average cost of production is falling. That's what economies of scale is. It ties in cost, long run cost. So economies of scale is as output increases, which you can kind of think of the scale of production to tie it back to the term. As output increases, long run average total costs fall. Diseconomies of scale is those costs are going up. Here's the picture just to kind of jog your memory from principles class maybe. the example I go through in principles class looks like this. We've got our good old-fashioned average total cost curve, which is presumably a short-run cost. So what defines the short run versus the long run? What's happening in the short run that makes it short?
At least one variable is fixed.
Good, at least one variable is fixed. So it has nothing to do with time. If you're running a photography shop out of your basement, that's a lot different than making tractors at John Deere, right? So it has nothing to do with time. It's all about the factors of production. In the short run, in economics class, at least one factor of production is fixed, whatever it is. Tends to be buildings or capital, right? Because labor's easier to change than capital typically. So something is fixed in the production process, similar to the example we just went through with that last problem. So maybe we could think about John Deere making tractors in a small size building. As their minimum point, if they're cranking out 1,000 tractors a day, is here. As business picks up, if they're able to ramp into a bigger building, they are consistently cranking out 1,500 tractors a day, then they need to building, let's say, right? So as they're in their existing small building, they can do 1,500, but they find that their costs are going up because it's inefficient with the amount of machinery and capital, the mix of capital and efficient. And so they get into a bigger building. And so they're able to drive down their average total cost in a medium-sized building to that. And so that's the optimal cost minimizing combination of labor and capital if production is at about 1,500 units. Now notice if the economy falls into recession and they're only producing 700 tractors, being stuck in this big building kind of sucks. The heating bills are higher, the whatever's higher. So that is not the best size building to be in the long run. If business is going to be at 700 tractors, you're better off in the smaller building. See what we're doing here? All right, so then the story could continue here if we got to producing 2 today, maybe we'd optimize to be out here somewhere. And so here's the average total cost curve with a large building. In the long run, nothing is fixed, as Blake just said, because in the short run, at least one thing is fixed. So we can imagine a function that represents our long run average total cost that would be the outer envelope of all of these short run ones. Right? In fact, there's an infinite number here. If we started drawing them, I used medium and large, but really there's an infinite number of sizes of buildings that we could pick in the long run. And so the long run cost function is downward sloping over this range. So over here we've got economies of scale going on. Now it's possible for this to flatten out, and if we run into a management constraint, maybe it turns up a little bit. So our theoretical long run average total cost curve is U-shaped, just like before. Where it's downward sloping represents where there is economies of scale. All right, so now back to this problem. It also gives us long total cost, long run marginal cost. At what levels will the firm face economies of scale? So what do we need to do? Set them equal to each other. Now, what ones do we want to set equal? What functions are we given in the problem? Long run total cost and long run marginal cost. So what do we need to do? We need to get the average, so divide that one by Q. So that is the long run average cost, this concept that I just showed you here. Then we've got the long run marginal cost, set the two equal to each other. It's just like what we did here, but now we're using the long run functions to find out what that point is, and we will find where it bottoms out. Okay, so you are always doing this. You need to change. Write down what this function is. There you go. Equals. Keep B. You got to be diligent about that because you're terrible at it right now. I want to see you get better at it. All right. So then we're going to find the average total cost. So we're going to take this function divided by Q.
Okay.
So then that's why it simplifies down to what I wrote up there. And then you're going to set the two equal to each other, the marginal cost and the average cost, to find the quantity where that thing bottoms out. Okay? You're missing, this is 22,000. Yeah, it's only 20,000. Yeah, and then set that equal to the marginal. So you're setting this one equal to, is this continued on here?
Yeah. This is the long run absolute cost.
Oh, okay.
The long run marginal cost.
Oh, okay, you set them equal to each other there.
Yeah.
Okay. And then you
Yeah.
continued it. Okay.
A little shorter.
Yeah, I think you're doing the right thing. Yeah, so solve for Q. As long as you did that, I'm not seeing all your math there, but yeah, that's conceptually the right thing to do. Okay, I saw Taylor. You had an answer. What'd you get? 150. That's what you got too. Okay. Oh. I get looking at you. Give me your camera. Come on. Attaboy. Okay. Did you guys get 150? Colby and Blake still working on it? That is the right answer. So this is, I don't even want to call it Q star, but we'll solve for 150. For this problem. These numbers are just made up. I probably shouldn't have even drawn it up in this graph. Okay. Don't need to be confusing it. But that's what we solve for. All right, so that's where it bottoms out. So diseconomies of scale with this particular function not like a flat spot here. It's so that represents the range of production. Up to 150 is where there's economies of scale. Past 150, it starts to turn up, and so that would be just economies of scale. The last concept from this chapter I want to introduce today is economies of scope. So instead of economies of scale, we've got economies of scope. Very common in businesses that if they increase their scope of production, so scale is increasing quantity, scope increases product numbers. So we get more into the multi-product concept. So this is multi-product. And the key thing is that if we can produce something such that the cost of producing two goods jointly is less than the cost of producing each one individually, then you've got economies of scope. So that's kind of the definition of it. So economies of scope is a situation where the production of multiple products is less costly than the production of each product separately. So this one's intuitive, right? That's why we see businesses. You've got a lot of fixed costs, some overhead. We're not using this restaurant during the day. It's kind of a bar area, and so maybe we should allow businesses to have meetings during the day in our banquet room or something, right? So we're kind of offering a different product to better utilize our capital in that case. So starting to offer multiple products is something we see tons of businesses do. In the production line, some equipment might be able to do multiple things. So we, as soon as we make production runs of one product, we twist and turn, put in new ingredients, and make a new product. So that is the notion of economies of scope. Okay, that is chapter 7. And we will call it a day there. Mark your calendars. We've got a couple minutes to spare today.